So last year we did some pretty easy calorimetry equations that we just sort of plugged and chugged and solved for a variable. And you have a few of those in your textbook, and you'll have some in your homework problem sets. But I thought I might do a couple examples of some more complicated ones to get you to kind of really think about what are we doing here and what can we truly solve and figure out by using calorimetry equations and the idea of enthalpy, heats of reactions and heats of formation and so forth. So this first example, the reaction between magnesium and hydrochloric acid, I don't want that arrow there. The reaction between magnesium and hydrochloric acid, the first thing I'm going to do is just write out my balanced equation, just so I know what are my products, what are my reactants. Again, just a visual picture for myself to figure out what I have. Now let's go through and look at my givens. So I have a mass. I have a couple different masses. 3.25 grams of magnesium, and I'm reacting that with 125 milliliters of hydrochloric acid. Now why am I sticking this with the mass piece? Well, I'm doing a reaction. I'm making a solution of magnesium chloride and hydrogen gas. I can make the assumption that the density of my solution is 1, just like water. So it's a pretty reasonable assumption to say that 125 milliliters of hydrochloric acid is 125 grams. The other thing I have is a change in temperature, a delta T. When you're calculating delta T, it is always final temperature minus initial temperature. So my final temperature is 25.6. Initial temperature 18.5, so I have a delta T of 7.1 degrees Celsius. I also have a heat capacity, and your book uses S, I'll use C just because that's what we used last year. They're both the same thing. 4.86 joules per gram degrees Celsius. So now I can reasonably figure out my heat of, I can plug this into my Q equation, Q equals MC delta T. Now before I do that, let me just kind of pause and take a look at this last part of the question. Calculate the enthalpy of the reaction. Well, what is enthalpy? Enthalpy, we use the symbol delta H to represent enthalpy. And I probably didn't say this in the last video, but it is definitely in your textbook. The symbol that we use for delta H and the units that we use for delta H is kilojoules per mole. When I'm figuring out the enthalpy of a reaction, I want to know how many kilojoules of energy are being released for every 1 mole of that particular reaction. So in calculating the enthalpy of the reaction, what I'm calculating is delta H. I'll use a little RXN. RXN is just short for reaction. What does Q give me? Q gives me heat in joules. So when I go ahead and I plug in these numbers, MC delta T, okay. How do you know you have your equation right? Well, do a little dimensional analysis. Your units should cancel out. When I solve for Q, and this gives me 4,417 joules, that is my heat, the overall heat, released by one part of the system, absorbed by the other part of the system. But this doesn't give me the enthalpy of the reaction. It just kind of gives me a heat value. Delta H is in kilojoules, so I need to convert this into kilojoules in order to use this information. Okay, so now I'm ready to look at my delta H because I've figured out how much heat I get from this particular reaction. Now the moles piece. Moles of what? Well, I've got 2 different substances, and here's where your knowledge from the previous chapter will help you. I'm going to figure out moles of magnesium. Why am I using magnesium? Because magnesium is the limiting reactant. Okay, and when I look at my balanced equation, I can tell that magnesium is going to be my limiting reactant. So I'm going to convert my grams of magnesium into moles of magnesium. And if this is a calculation that you're a little shaky on, please come in and see me, get some help. Okay, so this 4.147 kilojoules of heat that was released in this reaction, or absorbed, I haven't figured that part out yet, is due to the magnesium, because the magnesium is the limiting reactant. It's the thing that kind of rules the roost, that dictates what goes on. As soon as the magnesium is gone, the reaction is over. So when I calculate my delta H, I come up with 32.9 kilojoules per mole. Okay, I'm not quite done yet. Why? Because in the previous video I made a little bit of noise about you got to be careful with sign conventions. If delta H is positive, what does that mean? If delta H is negative, what does that mean? So if delta H is a positive sign, what does that mean? Is that endothermic or exothermic? That means your reaction is endothermic. Well, what if my delta H is a negative sign? That means my reaction was exothermic. So there's a couple different ways that you can determine whether your delta H value that you calculate is negative or positive. Your textbook has you kind of change the sign of the equation, and you'll sort of see that, because the heat of the solution equals, and their explanation is this, where they take the heat of the solution, and therefore that is the negative of the heat of the reaction, that the heat of the reaction goes into the solution and vice versa. What I tend to do is I stop and think about it. What happened? My temperature went down. My temperature went from 25 degrees down to 18.5 degrees. So was heat being released or was heat being absorbed? Well, if the temperature went down, that means the heat is being released. So my delta H is going to be negative. So I'm going to just go ahead and throw a negative sign in front of that. This is an exothermic reaction. Next example, calculating heat capacity. Now as I go through this particular example, I've got a lot of different challenges here because I've got a mass of copper and its initial temperature. I have a mass of water and its initial temperature. I mix the two together, and then there's my final temperature. So I've got to calculate heat capacity of the copper with one very important assumption, assuming that all heat lost by the copper is gained by the water. So instead of just doing 1 Q equals MC delta T, I've actually got to think about it in two pieces. Think about the water as one system, the copper as another system, and then I got to put the two things together. So I'm going to do one calculation with the copper and one calculation with the water. So what do I have here? My temperatures. Well, I'm going to calculate Q for my copper, my mass of the copper, 46.2 grams. My specific heat of copper, I don't know. That's what I'm going to be solving for. Change of temperature. My temperature started at 95.4. It is ending at 21.8. So my delta T is 73.6 degrees Celsius. Now the water. What's happening to the water? What's the heat absorbed or what have you with the water? My mass of the water is 75 grams. Specific heat capacity of water, I do know that. 4.14, some books use. 4.18 joules per gram degrees Celsius, so that's a constant. My delta T for the water. It started at 19.6. It ended 21.8. So final minus initial gives me 2.2 degrees Celsius. So if I go with the assumption that all heat lost by the copper is gained by the water, I can therefore set these two calculations equal to each other and solve for C. So I can figure out what the heat capacity of the copper is by equating it with the water. So whatever heat was given off by the copper was absorbed by the water. So that's how these two equations can also work together. And then I come up with, what did I come up with? 0.20 joules per gram degrees Celsius. Okay, so there's an example, just kind of using the idea that the Q of the metal will equal the Q of the water. The heat from the metal went into the water, and so that's how this calculation works.